Then we'll start. Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's it. Let me briefly introduce our speaker today. It is an honor to host Dr. Seong Kang, who is a distinguished professor of mathematics at the Georgia Tech, where she has taught since August 2008. She received her PhD in applied mathematics from UCLA in 2002. Her research focuses on advanced mathematical approaches to image processing using variational, functional, and PDE-based methods for tasks like denoising, deblurring, in-painting, and segmentation. She also explores numerical methods and scientific computing, including data clustering and the differential equation identification from limited data. In addition to her research, Professor Kang serves as the CSE coordinator from the School of Mathematics, overseeing both the CSE PhD and MS programs, and mentoring students interested in applying mathematical ideas to practical challenges. Today, Professor Kang will talk about identifying differential equations from single observations with numerical methods, IDENT to weak IDENT, and more. I'm sure we are going to hear a wonderful talk. Now let me, well, before I pass the baton to Professor Kang, let me ask a question. Professor Kang, we usually do so don't be surprised. Some informal questions before you actually give a presentation. So today's questions would be, if you can share any supernatural ability you have, like supernatural hobby, like not ordinary people might have. Yeah, if you have one, please share with us. Sorry for the unexpected question.
Oh yes. Now I feel like so insignificant. Supernatural ability. I'm just a normal person.
Yeah.
I'm just a normal person. I try to be kind in every day. And that's all I can say. So
Oh well,
yeah.
that's supernatural. I mean, personally, it's very hard for me to be kind. So thank you.
Try is the word. Try is the keyword.
Try. Okay. All right. Stage is yours.
Yes, thank you very much. So I would like to thank Dr. Choi for inviting me. I am very, very grateful to be presenting this work here today. And thank you everybody for coming and attending my talk today. I really appreciate this. Okay, so today I'm going to talk about identifying differential equation from single observation with numerical method. So the objective, the problem setup goes like this. So the initial motivation that I had was that this was like maybe like more than 12 years ago. I had this idea that when we observe something very interesting physical phenomenon, then let's say I just happened to take a video. I wanted to see if this from this video it can tell us what equation that this is. So that was the motivation. That how do we find the information from the single observation? This is the motivation. Now, I do emphasize on single observation because we may not have a second chance to record this phenomena again. And also, when we deal with the real data, we need to assume there are some noisy observation as well. So the motivation is to find this equation F, something like this, from the observed data. Now, this idea has been explored for a long time. So this is not an extensive list, but this is just like just to give you an idea. So especially in the biology, like a lot of identification of the system has been explored as early as 1969, and this is thanks to David Boltz. Shout out to Professor Boltz. that there are a lot of work that looking into these kind of dynamical systems, try to understand from the observation, what is your underlying dynamic. But since we don't know anything about the underlying equation, it is natural to assume or natural to think, what is the simple equation? So for this reason, we want to have maybe small number of terms expressing the equation. So naturally, sparsity gets into this problem. So there, the most famous work in this area, the recently using the sparsity, is the Cindy in identifying dynamical system. There are some theoretical works, and there are some work on PDE. Also, there are some work using the weak forms in this relation. I will mostly focus on ODE and PDE problems, but this problem can be also formulated or understood in terms of interactive law. So the agent-based method, different agents, there are many different agents, and how are they going to interact, and how do we find out the information from that? So there is some work in this direction. Also some machine learning as well. So you can kind of train the network to identify certain things. So for today's talk, we had a number of work on this direction of identification. So what I want to do today is that rather than focusing on one paper, I want to give an overarching idea of this direction. So we've been working on many different things. So there are certain things that we found out what is important in these this IDENT. So we've been calling this IDENT as a identification of differential equation using the numerical time evolution, but any kind of method, these are all using different numerical techniques to actually find it. So what I want to do today is that starting from IDENT, so this was our initial work. So this is going to act as a backbone. And I want to show what kind of improvements that we have made and what kind of things that we found out through this journey of exploring this idea. So hopefully by at the end of the talk that you will have a good idea about what is important and how we can do different things and what are the differences between some of the methods that we have been proposing. Okay, so let's start from the beginning. As I said, I do find it to be very important to have a single set of time-dependent data. And we all assume that this data is noisy. At the beginning of this area, some of the earlier work put in the noise in a different way, some interesting way, but we want it to be true to it. So we just add the noise from the given observation is assumed to have additive noise. So you have U plus an epsilon, something like that. As I will talk about this, noise is very difficult to deal with in this approach. So the denoising is very important. So that is going to be one part that I want you to pay attention. Now, since we don't know anything about the underlying equation, so it is beneficial to have certain assumption. So the first one assumption that we make is that this F should be a linear combination of some of the feature terms. So each term can be nonlinear. You can have uxx squared, ux or uxx. So you can have a nonlinear term, but still it can be represented as a linear combination is the assumption that we make. So these, when you have these kind of feature term, people ask, this is called, some people call this a dictionary. How do you choose this dictionary? And then when we started doing comparison, we realized some of the method did not use the full dictionary, but they sort of handpick certain things. So I just want to be clear that what we want to do is we really want to understand what is going on without any assumption. So systematically, we gave the dictionary. For example, it can have up to 2 multiple of the term, or up to 6 multiple of the term, up to 2 second derivative, or up to 5th derivative, or 6th derivative. So once we make this decision, we put in all of these terms in the dictionary, and we're going to call this to be a feature term. So in this case, this example is up to 2 multiple of 2 second order derivatives. So these are all of the terms that which is represented when you allow this to be 2 multiple and with the second order. In the experiment that we did up to fifth multiple or sixth derivative, so at the end, some of the dictionary was 190 terms and so on and so forth. So, but we tried to be consistent without giving any bias at the beginning. Just because we make this assumption that given data U can be represented as each column. So this term is going to be constant term. This term is going to be U, and this U is going to be the given data. U square, you just multiply it twice. UX, you have to approximate. Now you have UX squared, the UX is approximated, and then you square it. And then UXX has to be approximated. So all of these feature terms that we put in, we have to approximate the derivative. Now, if you write it in this matrix form, that this A, coefficient A1, A2, A3, A4, this can be represented as a vector. We're going to call this to be a coefficient vector. Throughout this talk, I'm going to use two terminology. One is support and one is a coefficient value. Support meaning we assume we allow the equation to have any of these 10 terms. So if we identify certain term to be non-zero, we'll call that to be a support. So for example, if you have a Burger's equation, then you will have A6, this term to be identified. So only coefficient A6 is going to be non-zero. Everything else is going to be zero. And we will call this to be a support. And we still need to recover the coefficient A6. So then we'll call this to be a coefficient value. And you have this term, which is F times A, and B is going to be our UT. So this is the time, the way how this is dynamic is changing in terms of time. And this is represented by B. Also, it needs to be approximated by some approximation, numerical approximation for that. So this talk has no deep learning, there's no training. And as I said, we're just going to have one single observation. And this work is really about how far can we go without learning anything from one single observation. So oftentimes our time can be shorter than some of the other cases, but whatever, the time might be short, time might be long. We're just doing our best to find the best approximation. Okay, so let's start from the ident. This is because to give a backbone of this, this idea. From the given discrete data, this is the U, this is the only thing which is given, but this is time, changing in time, as well as the space is all given. We construct a feature matrix, as I just explained, and then we have a vector B, which is UT. All of the derivative approximation in each column for this work, we did ENO scheme. So ENO 5, in fact, because we wanted to guarantee up to second order derivative will be second order accurate. So we use ENO 5 for each column whenever you have a derivative. And then we needed to denoise this. Denoising is really imposing a lot of challenge to this process. So we will pay attention to that. In this particular work, we use moving average least square. After that, as a first work, we tried the conventional thing, meaning that we add the L1 minimization and we use lasso. So the coefficient itself is supposed to be sparse. That was the underlying assumption. However, we found that that was not enough. So throughout this process that you will see, we do use sparsity, but oftentimes the sparsity is not enough because of the noise, because we add noise because of different variation. So we do add a second step of model selection. In this case, we use what is called time evolution error. So among this result, we're picking the one. And then after we pick the support, so we've identified the support, then we identify the coefficient by least square because we already know which terms are non-zero. So only letting those terms to find the value, then we do the least square. Now, we have a very consistency. First, one important thing is the least linear system. How do you set up a linear system is important. And how do you do a denoising is important. After that setup is done, we are going to do the support identification. This is the actual equation identification. And after the support, the equation itself, form of the equation is identified. Then we're going to find the coefficient by just least square fit. The given data, you just fit it. So this is consistently, you're going to see this three things, which is the main backbone of this. In IDENT, we use what is called moving average least square, because at the beginning, we wanted to try different type of denoising. We tried least square fitting, we tried moving average, but moving average least square seems to be the best. I know a lot of denoising method because my background is in imaging, but we didn't use any of this method, but we used the method which we can guarantee the order of recovery. So in this work that we assume, we prove that if it is a third order approximation of the smooth function, then the moving average least square will keep the same order of approximation. So, but you can generalize this to higher order. So we wanted to have an order guarantee of the denoising. So that's why we use the moving average. So this is an effect. Let's say you're given Berger's equation, and then this is time dependent, and you have a noise. So you have 8% noise. Now, if you use L1, the lasso that we use, these are the coefficient that comes out, which is non-zero. This is Berger's equation. So the correct term should be UUX, but that term is actually 0. So there are three terms which is identified, which is completely not related to the underlying dynamic that we're looking for. So there's no denoising, then it's bad. So it's very difficult to do. So when you apply the denoising, we use the moving average least square. So you do a denoising on the data itself, just denoising once. Then when you do the L1 minimization, you will have these three terms coming up. If you do the lasso, in this particular case, the coefficient of UUX is the biggest. So you might simply think, okay, how about you threshold it? But it's not as simple as that. Sometimes this coefficient that this is identified to be non-zero can be very high. So we find it to be not enough to actually just consider the threshold, because the result will be dependent on what kind of threshold that we are enforcing. So this is when the time evolution error comes in. So what we did is that, okay, we take all non-zero, 1, U, and UX. So you have three terms. From these three terms, consider all of the PDEs that you can make with these three terms. UT equals to constant. UT is equal to U. UT is equal to UUX. UT is equal to constant plus U, constant plus UUX, UU, and then constant UUX. So there are 7 equations that you can consider by having these 3 non-zero terms. We consider everything. So now what do we do? From here, among these 3 equations, you find the coefficient by least square. In this case, we didn't do anything special. You first find the coefficient. For each equation, we find the best one. How do we find it? We just take the initial condition. You're given a data which is time dependent, so you just take the initial condition and then plug it in. You regenerate, numerically regenerate the evolution for all these 7 equations. So from the initial condition, and then you generate with a small delta t, and then see at the end it matches up. Which matches up the best, we pick to be the best one. This is really a fundamental of the numerical convergence, basically. So you evolve with a smaller delta t is very important. So among these 7, you check it just at the very end, at the beginning, at the end, and then whatever gives you the smallest error, we pick it. So this is how we pick the Berger's equation for this case. So the reason for having a t is because L1 minimization is not enough. Usually it gives you 0 coefficients for non-zero 1 and non-zero 0. It should be 0, but it gives non-zero. And then it depends on the thresholding. It depends on the lambda and so on and so forth. So this is why we add the model selection as a time evolution. But I will show you many different cases for that. Okay, so many different. There's a 2 fundamental idea behind the time evolution error. One is a numerical convergence. This is what we teach, right? In the numerical PDE. If you have a converging method, then it has to be stable and consistent. So if your delta t gets smaller, at least it needs to get closer to the equation. So this is why we regenerate the data with smaller delta t and see if it actually matches up. Another reason is that in nonlinear PDE, you cannot say, go to each term and say, do you exist or not? Are you yes or no? Yes or no? You cannot do that. In nonlinear PDE, you have to work as a set. So you need to really work as a set as here, like U, constant and U and UX. You have to consider this as a set and see if this actually matches up. But this time evolution error is very slow, as you can imagine, right? The complexity. So you give an initial condition and you have to wait until evolve all the way to the end. So this is red is one example, green is another one. We picked a small one, but we do better than that. So this is being inspired by the shooting method. You have shooting method, multi-shooting. So we do multi-time evolution. So in the robust ident, we move from this and then we do multi-shooting. So in multiple location, you evolve the same equation and then add these error. So idea is fundamentally same and then also similar to multi-shooting. So then your time evolution has to be done in a small time. So it gives you a saving. And also you can do this in parallel. So this is one model selection. So in the original ident, so this is what we showed. That having a denoising gives much better error than no denoising. As the noise level increases, that it is significantly better to have a denoising method. In this equation is Berger's equation. Now, Berger's equation looks like, oh, okay, this looks pretty well. It works pretty well, up to 30% noise. However, in this equation, if you add a little bit of diffusion, like a viscous, the Berger's equation, it starts to not work as well. This can only handle up to 0.05 or something like this. So the reason is this. So in this paper that we have an error analysis showing the difficulty of this problem. So this is the sensitivity to the measurement noise. So what basically says is that if the underlying equation is higher order, it is that much difficult to find it. It's because of the denominator. So if your underlying equation has fourth order, fifth order derivative, it is that much difficult to find, especially because we are assuming there are noise to that. So this shows the difficulty. So how do you move forward from this? So we learned something from this. So now we move forward. In the previous ident that we found out denoising is important. Now, but if you look at the denoising, this is the effect. This is the initial U, and then you have a very, very small noise. Now you approximate this is a derivative, then the derivative noise gets emphasized. If you consider the second derivative, the noise gets even more emphasized. So we developed a better denoising method. So what is called SDD, successive denoised differentiation. So every time we do a differentiation, we're going to do a denoise one more time. So given the U, you denoise it. And then you have a derivative, so derivative approximation, you denoise it one more time. If you have K, you do that. So you smooth differentiation, smooth differentiation, and so on. This sounds really, really crazy, right? But we can show that under that assumption, some small assumption, the smaller assumption is that polynomial has to be degree S. And then the method of approximation should be accuracy at least S minus 1. Then we can recover this to be S minus 1. So it sounds really crazy, but successfully doing has a benefit to that. So in the robust ident, so we made two improvements. One is the denoising. So when we're making a feature matrix, we denoise it better. And then the sparsity we improved also. What we found out is that in L1 minimization, that there are terms that which comes out with a very small coefficient which we cannot control. So rather than going into that route, we just gave them. So what we did is, okay, K is equal to 1. Find the best column to represent this given data. K is equal to 2. Find the two best column to represent this. K is equal to 3. K is equal to 4. K is equal to 5. We do all of this for each K. But the subspace pursuit requires the sparsity. So we have to do everything. K is equal to 1, K is equal to 2, K is equal to 3, K is equal to 4, and so on. So now among this, now we need to choose the best one. So again, the model selection. So we use the sparsity, but we accompany this by a model selection. So how do we do it? In this case, we did the multi-shooting, as I explained earlier. However, we found out the subspace pursuit itself is more stable, but even cross-validation was good enough. So what is cross-validation? The cross-validation is that, let's say that much data is given, so you cut it in half. It doesn't have to be half. We can cut by alpha. We also analyzed it in the paper. Let's say you roughly cut in half, and then use this to find the coefficient and use that result to fit, right? So you just cross-validate what is the best one. And in this case, then you can choose among all different K, you choose the best one. So once you choose it, that's a support. And from the support, you find the coefficient by least square. It's the same. So I hope you see the trend right now. So linear system with a denoising is important. And then after that, you use a sparsity, but you need to use the sparsity in a correct way. And then after that, you do the coefficient identification by least square fit. So this is some of the results. So in the robust ident, so you can handle some discontinuity. Discontinuity is because we use the ENO scheme. So you can handle the discontinuity, the noise with 10% noise or 30% noise, but still it can identify. So here 10% noise, this is the equation which is identified. 30% noise is identified. The true equation is UT is equal to negative x squared on top here. And then these are the recovery with a 30% noise. We can do this with a Burger's equation with diffusion because this can handle up to 5% noise and maybe a little bit more. But this comparison was meaningful for us because in IDENT that we could only do 0.05. But just because of this SDD and using the cross-validation that we were able to get to this. We can also enter third order derivative. Now from here, how do we go forward? So the next part is the weak ident. Around this time, actually, there were multiple work which is using the weak form. So, okay, so we decided to try this as well. Yes, oh, thank you, David. So yes, so the weak form. Now, one of the best part of the weak form, the difference between the ident, robust ident, and the weak ident is that it's a differential form versus integration form. So the weak form is a numerical integration. Another beautiful part of this weak form is the test function. If you use the good test function, this can suck up a lot of the difficulty from the differential equation. So that is important. Now, from here, we can do even further. So I talked about how to find the sparsity and modal selection. We improve that even. So we improve this with a narrow fit with a trimming. And then we can also do the coefficient identification even better. Okay, so going back to the consistent scheme, now this is the linear system is important, and we set it up as a weak form, and denoising is coming from the weak form. Now the sparsity is important, so we use SP. In this case, by using the narrow fit and trimming, which I will explain, you can improve upon this result, and then we can get the coefficient also to be improved. In the weak ident, there is about 4 things I want to emphasize. Number 1, the weak form. Now, weak form is great because of this. The weak form is great because of the integration by part. You're setting up the equation, the differential equation is given, you multiply this by a test function and take an integral. And then after you take an integral, the key point is that you need to do an integration by part such that all of the derivative needs to move to the test function. Because of this, in order to truly benefit from the equation, truly benefit from the weak form, your equation has to be a certain form. So it needs to be u to the alpha, beta power to the alpha derivative. Then you can really benefit from the weak form because all of the integration part will take up in the test function. Because test function is the one that we give. So we can give a very nice test function, which is smooth. So that is one benefit. So yes, shout out to Messenger and Boltz on the test function, because when we started looking into this weak form, we tried many things. We tried different test function and so on. But this test function really works very well. So the way that we understood is that there's a denoising effect because you're trying to match the polynomial, the shape of a Gaussian. One thing we found out is chopping is not good, actually. surprisingly, chopping is not good. You need to sort of suppress it in a right way such that it will achieve denoising at the same time. So there are certain things that you can look into in this test function. So you don't need to compute the derivative, and then the approximation of the numerical integration can be higher order by whatever the method that you use. That's the first thing. Second thing I want to mention is that what we found out is that this feature matrix, where this is W because it's a weak form, the feature matrix needs to be sort of well conditioned. So another thing we found out is that each column needs to be normalized in a proper way. So in fact, in this paper, we introduced two different kinds of normalization. One is the error normalization, which is presented here. And what is also a column normalization, which is needed for the SP. So how do you normalize a column? This is also important. So in this particular case, what we are mentioning here is that depending on the feature term, your error might be different. So we wanted to balance it. If you have like a higher order or not, we wanted to balance. So this is the term that which actually we can explicitly compute the error term, the leading coefficient, so that we error normalize each column for that. So this is the weak ident. So you have a weak form, the feature matrix, and B, which is UT, and you're trying to do the SP. Okay, so you do the subspace pursuit. Now here we added what is called narrow fit and trimming. Okay, narrow fit and trimming. What is narrow fit? Up to now, all of the coefficient recovery we're doing, we've been using the whole least square from the given data. That's all we did. But actually, we can do better. So what we found out is that given a data, there are regions, there are more dynamics than the other. So for example, this is the image. They're sort of flat-ish. And then there are some places that there are some dynamic. These places doesn't really contribute too much, but you cannot get rid of everything. So what we do is that we identify the high dynamic region, which is given by the high dynamic of UX. We also experiment with a different feature, but in order to identify the dynamic, how much it is changing, U needs to change, right? And then UX needs to change. So this is why we find U and UX to be the most meaningful to indicate what's the high dynamic. So we just find the region that which there are a lot of variations. So this yellow is the part that we're going to use. So given data is this much, but only the yellow we fit. So the fitting of the least square even gets smaller now because we are only doing a smaller region. And surprisingly, the coefficient recovery gets better. So the high dynamic, we found it to be important. Now trimming. As I said from the beginning, because we're using the SP, subspace pursuit, K is equal to 1, K is equal to 2, K is equal to 3, K is equal to 4. All of this needs to be computed. But some of them you don't need, because when we're doing least square, the more terms you have, better approximation is going to be. But that more term may not be meaningful. So how do you do it? So we trim. Some of them, which is not important, remove it. How do we know what is important or not? How does it influence our UT is the key. You have a column of UT, but you added a new column. But this one contributes really minimally to the dynamic. UT, we get rid of it. So this threshold was just 0.05. And then for each sparsity level, we're computing. But as you can see, quickly, it converges to the right one. So even if we need to, we allow to find sparsity up to 40, because this dictionary was like 100 and something. So we ran up to sparsity 40. That's because of that. So we have a really, really large dictionary, but still it kind of removes it. So you don't need that. So it quickly converges to what you need. So this just shows the comparison. So in the PDE, we try these equations, like 2D equations and then double derivative and so on, fourth derivative, and it works well. When you don't have noise, a lot of methods actually work well. So we get very similar result. This is the true one, and these are the results. We did compare to IDENT, also the SP, the robust IDENT as well, and weak IDENT is much better. Now, this is the coefficient error, actual coefficient that it works about. Now, this is noise level 1, meaning 100%. We add 100% noise. So as the noise level increases, then you can show some benefit. So then you can show. We systematically did it. So for each different noise level, we ran like 50 times and then showed the variance of it. So this is the noise level and so on. And then this is the true positive and then the false positive and so on. And this WPDE was the Wixindy PDE. And this is also two variable with the second order derivative and so on. Then this is the equation that we recover. It looks quite messy, but the true value is 1, and this is 0.99. This value is 1, 0.98. So it's actually quite close. So we represent the coefficient error is the L2 norm, and the difference is 0.03. So that's what I want to show. We also applied this to ODE. Most of the work we did on some PDE, but we also tried with the PDE. For this experiment, we found out that this doesn't have any derivative terms necessarily. So we didn't find this to be particularly difficult, and we chose these to compare with other methods. So the red is the given data, while the black is the true data. So from the red dots, the noisy data, that we were able to recover green. So that's the green that we recovered. From the red data that we recovered the green, and these are the showing the coefficient error, which is shows a good recovery. Okay, so this is also comparing with the ODE. So this is weak IDENT. This is the weak Cindy ODE, and we did compare to Cindy because this was ODE. So the dynamical system that we did compare. So this is the proposed method with an error with a small variation, but sometimes you have a lot of variation. This is because we ran like 50 times for each noise level with each time running that you will have a different noise. So this is the reason. So this is sort of a representative result for that. Okay, so how do we move forward from this? So now this work is on Fourier ident. So now Fourier ident is because in the weak ident, to do the test function, we actually had to solve it in the Fourier ident at the beginning, but then you come back to physical domain. So here we said, okay, how about we continue in the Fourier domain? Can we find out something? Now here, like if you go to the Fourier domain, you can do it, but it turns out this is much difficult, this is more difficult than the solving things in the physical domain. The reason is the value of the response is all over the place. So some response is really big, some response is really small. So it's a very big variation. So we find it important to reduce the domain. So now in Fourier space, what it boils down to is to chop the domain and then only use the meaningful information to do it. So that is one thing. So one meaningful region. And we also use the subspace pursue, but also use the co-region. I will show you in the example. And then we also find what is the best one. We also use the group trimming and then also find the best data to fit. So the least square fit, even we are moving forward a little bit from that. So this is just to show the consistency of the work that we are doing. So linear system, in this case, in the Fourier domain. Denoising is done in a Fourier domain by the domain partition. The sparsity is important that you identify this. And also we use the frequency domain partition and then find the best result. So there's 3 steps that it is consistent. One thing I can say is that the error analysis, the one thing is interesting is the error analysis. In the initial, at the very beginning, I showed you the IDENT had an error term like this, that you have an epsilon. The noise can get emphasized if the underlying equation is high order. But if you use a weak IDENT, it becomes a linear form. This is the same in the Fourier as well. So when you use the integration form or so you have sort of like a kernel-based method, then the error can be small. It can be less dependent on the the order of the underlying equation. So that's what we were showing. Just to briefly illustrate, so this is SP, so the subspace pursued with k is equal to 1, they identify the one best column. At k is equal to 2, they identify two best column, and then 3. Now you go to fourth one, so let's say k is equal to 4, you find 4 terms. Now you found the 4 term, but there is a score that we compute. One of them is so small, so we cut it. Yeah, you're not so important. And then you update. This becomes the same as the sparsity 3 one. And then if you go to 5, the same. 2 of the 1 is not as important. So then it goes back to 3. So even if we allow to find sparsity up to 10 or 20, the trimming really helps to kind of give the meaningful one by removing the unimportant things. Now, this is showing the effect of the using the frequency domain. So the frequency domain is this large. But if you follow the theory of the Fourier analysis, if the underlying data itself has a certain smoothness, then the coefficient has to die down in a certain speed. If you consider that region, that is this red one. So this red one is the only meaningful region that you can guarantee from theory. So this red region is zoomed in here. So this is the only meaningful region. Even within the meaningful region, for each feature term, some might be noisy, some might be not as important. So we even partition that and only use these regions. And you can get the coefficient recovery to be really accurate in that way. So this is the coefficient, right? The coefficient value recovery improvement. One of the best part of the Fourier ident is the Fourier ident can be comparable to weak ident as well as weak Cindy. So if you look at the paper that we have a comparison, one of the good thing about the Fourier ident is that if your initial condition or given data has many, many modes, even if you have really high level of noise, that it can still be better than other methods. So that is one of the benefit. In some level, I guess it makes sense because you're using in the Fourier domain. Just to quickly summarize what I talked about up to now is this. Given a single set of time-dependent data, whatever it is, it may not be enough data, but we will do our best to give you something meaningful. So single set of time-dependent data, which is noisy, and noise and higher order derivative, higher order underlying dynamics makes it difficult. However, if you set up the linear system in a good way, you do the denoising in a sophisticated way, and if you use good denoising method, that will help. The support identification, you will need some sparsity, but also model validation can help. We found the subspace pursuit to be better to deal with because it's concretely telling how many terms and so on. And then this is accompanied by the model selection using time evolution error, multi-time evolution error, cross-validation, as well as trimming. These are all fundamentally given by the numerical PDE, the idea of numerical PDEs. And using that, we're trying to validate the model, the select. Coefficient identification is always done by the least square fit. But from the weak ident, we learned that you can even look at the high dynamic region to even improve the coefficient. And also Fourier ident, you find the meaningful data to fit it, then your coefficient recovery can be even improved. Now, in this sense, I do want to be clear about this. So one thing I can say is that why do I talk about ident, robust ident, well, while I have this method, right? So for example, if somebody asks me right now, say, I don't care about any of this, give me one method, I just want to try it, then I would say use weak ident, okay? So weak ident is most stable, so I will do that. Even then, why do I talk about ident or robust ident? The reason is the ident and robust ident can handle any terms, any boundary condition. But in order to take advantage of the weak ident or Fourier ident, the data should have a periodic boundary condition. So what we do is that rather than changing the boundary condition, we pad it. We pad, and then so that we don't lose information, but we make this periodic. So we mentioned this in the paper. And also, in order to take advantage of the weak form, you have a certain form that we need to have. A lot of the equation people are interested, KS equation, KdV, and all of these things is in this form. So yes, so if you are looking for these things, you can use weak ident. However, if you want to be really free, you want to really give any kind of method, I still think the ident and robust ident, we can try to improve this so that we can handle any term. One last thing I want to briefly mention is that up to here, all of the equation that I'm mentioning is about finding one equation. Given one set of data, one equation. But who says, right? What if the equation itself is changing, right? So I want to talk about varying coefficient. So in the original ident paper that we also had that, and then we also have a group SP. So let me explain. So variable coefficient of differential equation looks like this. You have a certain equation. At the beginning, maybe you start out with a diffusion equation, but then it suddenly changed to transport equation. It includes that because we are allowing the coefficients to change from 0 to non-zero or non-zero to 0 and things like this. So how do we model this? One of the classical method to use is finite element. So we give an element. Okay, so we give an element. So this coefficient, used to be a constant, now becomes a finite element, all of the elements. So now you can imagine this feature matrix gets significantly fatter, right? It used to be one column. Now this one column is representing one element. So for each element, you need to have a copy of yourself. So you have a constant, you have L number of bases, then you will be expanded to L number, and you have U, then U will be expanded, UX will be expanded. So everything is going to be expanded by the number of your basis function. That is represented by L. But how do you do it? But this whole chunk is the same anyways. So we use a group lasso using this as one chunk. Now here, what we use is that we use group lasso, but we know that's not enough. So how do we did the model selection? The model selection is added by increasing the number of basis function. Okay, like this. To have a linear system, it needs to be denoised in a proper way, but this one was the initial ident, so we used a moving average least square, and we use a support identification using the group lasso, but you improve this by using what is called base expansion. In the numerical PDE, if you increase the number of basis function, your approximation should get more accurate. So that's the idea. If you increase the number of L, does it get closer to the given data? That is how we pick. Now, how do we move forward from this? Because we did SP, the subspace pursue, now we have group subspace pursue. So we use the same basis function, the base element, and then we use successive denoising, STD, because this is after robust ident. And then we use the group SP on it. Now, among the group SP, we still have to have a model selection. In this case, we use a reduction in residual. So same, linear system. How do we set up a linear system in a good way? And then how do we use the sparsity and the model selection? Group projected SP is actually different from block subspace pursue because we are actually projecting to the projected space. So that is the difference. So this is mentioned in detail. So from the feature matrix, so just to illustrate, each feature matrix is fatter because for each element that you need to have that many columns. So each element is fatter. You put this into SP, group SP, K is equal to 1, K is equal to 2, and so on and so forth. And then we find the one which gives you the first big drop. So that's how we find it. And then you do the least square. So this is the trajectory. This is one given image, given feature that where the coefficient is changing from one to another. So this is true coefficient for UXX, and this is true coefficient UUX. And then if you use a group SP, so this is no noise case, this is the error of the coefficient. Okay, so there's some fluctuation, but they're pretty good. If you add the noise, then it does find the coefficient, but at the end there are some places that which is not accurate as well. Because IDENT itself is very difficult, and we're doing a finite difference, and we're allowing many more parameter to be chosen because of the element, these problems are very difficult. So there's not exactly same work in this direction. However, we sort of took something similar to compare. So what we found out is that as the noise is increasing, as noise level is increasing, then it starts to find more unnecessary terms. But if you use a group SB, that still, even if it goes to like 6% and so on, that it still identifies the correct term. The correct term meaning that some term may be 0 or not 0 at some point, but including that line. If there's any non-zero term in the time evolution, that this will be identified. This is the size of the dictionary. This is difficult to do, have a big dictionary. So the dictionary 1 is only using 35 terms, 56 term, and 330 terms, but consistently group SP will be able to identify the correct term. Okay, so to summarize, given a single set of time-dependent noisy data, identifying an underlying equation is very difficult problem. However, if you use a numerical approximation in a clever way, a lot of numerical techniques can contribute to this work, and I think you can benefit from it. And the sparsity needs to be handled with care. And a lot of the coefficient recovery has been done by least square, but which can be also improved as well. So yes, so that's all I want to say. Thank you.
Thank you so much for the wonderful talk, Professor Kang. Let's have a Q&A session. There are a bunch of questions in chat room. Not sure you can see that or not. Starting with Russell, he asked, why do we not check the error at the intermediate time? So I think he was asking these questions in the beginning, before you explain about the multi-shooting stuff. Yeah, if you can handle that question, Professor Kang.
Yes, thank you for the question. Yes, you can check intermediate time. So you're absolutely right. So from the beginning at the end, in IDENT, the reason why we check at the end is because to give enough chance for the error to grow. So if there's a wrong term that we wanted this to grow, that's why we give the full benefit to check at the end. But as I showed you for the multi-shooting case, you can do it in the middle, so that you can sum this to kind of show the difference. I hope I answered this question.
Okay, thank you.
Oh, 3D. So how about 3D PDEs?
Oh, yeah.
Yes. Even, to be honest, even 2D is very difficult, especially when you go to the varying coefficient is very difficult. 3D extension, I do think it is possible to do. But if you go to the varying coefficient, it gets much more difficult. But it depends on the problem. If the equation is, so for example, let's say data is given, but data is given in like 3D PDE, but the data itself is so boring, then you may get a very simple result. But if the data itself is rich enough to handle all this, then they will try to find something. So I would say can it scale to 3D? Yes, probably. There are some computational costs because of the size of the dictionary, but we're introducing many methods to stabilize it. So I do believe the 3D should work, but it depends on the data. The data needs to be given with enough information. Yes, the multivariable. Yes, it's the same question. I hope I answer your question.
Thank you. Yeah, thank you.
Awesome. Okay, next question is by Luning. Yeah.
The periodic padding.
Well, can we state the question
yes,
first?
yes.
So that, because it's recorded on the YouTube. people will appreciate it.
So the previous question was, how about 3D, PDE, or multivariable PDE? So that's how I answered it. Now, the next question is that I wonder how did you adjust the periodic padding if the original field boundary condition is non-periodic? That's correct. Yeah, this is a very, very important question. Using any value of a padding, introduce the false gradient between one of the boundary padding. Yes, that's right. So this is a very good question. So what we did was that we made a copy and cut it in half, and then we flipped it, right? So we did flip. But you're right. The derivative around the boundary may not be as accurate as the other. So it is true. But we didn't see too much of this effect. Again, I think this will depend on the data, meaning the boundary information is so heavy, then this will. But most of the dynamic is happening in the main domain, then this effect will be minimized in a way. So, but yes, there will be some the loss in the information.
Awesome. Okay, the next one is Amit. Actually, Amit, do you want to unmute and ask directly?
Sure. So very nice talk. Thank you for summarizing all of these methods. We are trying to learn PDEs, three-dimensional PDEs for systems. Like we want to train or discover mesoscale continuum models from atomistic data. So everything is in 3D. And the general assumption, when we look at all the PDEs that are out there, the general assumption is that only either the first order time derivative or the second order time derivative is enough to capture the time evolution. But I wonder if you can tell us something about PDEs where you have, let's say, first and second order time derivatives present, or if possible, higher order time derivatives present, and situations where the time derivative is coupled with spatial derivatives.
Yes, this is a very, very good question. So yes, we did suffer with this in a way. So it's not so because of the initial motivation that we had was to see the dynamic. So we didn't really look into too much in terms of UT and UTT or things like that. So we didn't really look into that part very carefully. However, some of the weak form models that they do have UT and UTT in it. So it's matter of the column. So what you want to anchor against, and then you can put any column, any kind of feature that you want. So you can put UTT in it, you can put UTUX in it, and so on. But what you get at the end is a least square. So how well do you fit the data is what it means. What will give you the result. Did I answer your question?
Sure. I think that's what we were trying to do. But I wanted to see if there are other ways to formulate the problem. But anyway, I think your suggestion is good. The other problem is this is related to what Faye had asked about the 3D systems, is that everything looks nice, well, relatively nice when you handle 1D systems. The moment you go to 3D systems, at least for our case, we are finding that the matrices are severely ill-conditioned, in the sense ill-conditioned, and because we have a large dictionary, they are rank deficient. So we have looked at close to 20 different, or maybe more than that, different sparse solvers, and believe me, the results are all over the place.
Yes.
So the question then is, how do we, for severely ill-conditioned, rank-deficient linear systems, it doesn't seem straightforward to come up with a solution, like discover a PDE. Any thoughts on that?
Right. Yes, you're absolutely right. So this is the reason why we've been using SP, is because the idea is that just find the one best one, but the subspace pursuit basically is the least residual. So you look for one column that which gives you the least residual, two column which give you least residual. So this is the reason why we put k is equal to 1, k is equal to 3, and k is equal to 4, and we list all of this. And then this is why we introduce trimming and so on, because it's difficult. You're absolutely right. So if you use like a different type of sparsity in a different way, it's going to be all over the place. And this is what we observe also when we use like a lasso at the beginning. So this is why we accompany with time evolution error, multi-time evolution error. All of this is introduced for this reason. So I completely understand where you're coming from. So this is the reason why we were just doing one by one concretely, and then suggest a good way to pick among that. So that is the reason. Did I answer your question?
Yeah, thank you so much. Appreciate it.
It's a hard problem to begin with, so I understand.
Okay, got it.
Okay, thank you. David, do you want to unmute and ask question?
Hey, Sonia. Very
Hi,
nice talk.
David.
Hey, always impressed with the what the results are here. So I have a question about you were using lasso, and so one of the things that when we had looked at lasso and some other methods of that type a while ago, one of the things that came up is that there seemed to be some issues in satisfying like isometry conditions, and I was wondering if you had any thoughts about that, if it was working for you, or it seemed like when we were using those methods, they weren't working very well at all, and it seemed like that was the source of it. And so I was just curious if you had we hadn't looked at it in a while, so I was curious if you'd looked at it and seen anything.
Yeah, thank you for this question. Yes, so in that paper that when we were looking into it, so what it boils down to it actually, like maybe I didn't emphasize this enough. What it boils down to is the coherence of it. So let's say we have, let's say 330 matrix, right? That you have each column. They were all coordinated to each other. Then any type of lasso is not going to work well. So the column needs to be independent enough, then you have a chance. So now SP, is it better? Well, in SP that you may get random things, right? Like if you have one or two, because if they are correlated, you might pick one versus the other. But at least in SP, they will give you the least residual one. But I'm not saying it's perfect either. But yes, the one thing that I didn't mention too much is the coherence among the columns does affect the result of lasso or L1 minimization. So that is the difficult part. Yeah, I hope I answer in some way.
Okay, well, thank you. Thank you so much. Is there any other questions? That's all we have seen so far. If not, let's thank our speaker for the wonderful presentations and the great Q&A sessions.
Thank you so much, everybody. Thank you for coming to my talk. I really appreciate it. And it's nice to see a lot of people that I know. Thank you.
Okay, awesome.
Bye. Thank you.